Okay, so this is where we left off on last time, which of course was the last time we met, which was Thursday, excuse me. Good morning, ladies and gentlemen. It's good to see most of you today. Oh, good to see all of you, but good to see you today because you have an exam. So that's one thing we're going to go on talking about today. Let's see, the exam is going to be in the same location as last time, so that was Haggerty 180 for most of you. I think all of you was Haggerty 180. Okay, and I'm going to wrap up chapter 20 or chapter 19 today. Talk a little bit about the exam as much as I can, I guess you could say. I think you do fine. Don't be anxious. There was a question about these videos and this Camtasia things I'm putting together. I'm going to have chapter 15, 18, and going forward ready for you for the final. So when it comes to like Thanksgiving weekend, expect like a list of YouTube links for you to look at while you're with your family or wherever you're going to be. Okay, so I'm going to go ahead and finish up chapter 19 like I said before, and then we'll go ahead and do a little bit of the more substantive part of the review, I guess you could say. All right, so if you have notes for 19, our goal is to try to figure out a confidence interval and test statistic for this situation, where we're going to look at the difference in two sample means, right? All it is going to be an extension of what we've done already, so not so bad, okay? So what we're looking at here is, and I'm trying to minimize the number of blanks you guys got to fill out. So the same kind of conditions still apply, and quote unquote, yes, this issue is relevant for your exam as far as whether you're going to have a simple random sample, right? That's the word we're going to look for here. Okay, good. It's working. You working? Good. There. So it's a simple random sample. Okay, and then here's what's a little bit different now in this particular chapter, chapter 19. You see blank, so it's probably important. Do we have two simple random samples, right? And the key thing here corresponds to independence of the events. So we have two different groups of people. And then, of course, we're going to assume that things are from a normal distribution. But because we have two groups, then we're going to say that the proverbial that the sum of the sample size is less than 15. So we have two groups, so we got to look at both of them together. Okay, so you may have a group of 8 and a group of 17 that works, a group of 8 and 7 that works also. So that's what's different in chapter 19, is looking at the sum of the two sample sizes for the two different groups. The rest of it kind of just follows from that. And again, if the sum of the sample size is less than 15, you do this. Same kind of thing as before. We just had one group, so if there's no skewness or outliers, then you're okay. If the sum of the sample size is between 15 and 40, and we don't quite know if it's normal, that's still fine. So this will help you with your test for today, or just for the knowledge in general. When the sample size is less than 15, you need two pieces of information, right? If sigma is not known. You need normality, and you need no S/O. Skewness or outliers. No skewness, no outliers. But then when the sample size gets between 15 and 40, normality is not really as much of an issue. But the key thing here is no skewness or outliers. That's the same thing in chapter 18 and 19. And then once we get to 40, 40 is like the magic number. It's all good. All right? even in cases when it's skewed. So it's not as we gave you that as that sheet of paper with all the different criterion, but when it's normal and it's no skewness, no outliers under 15, you're good. No skewness or outliers between 15 and 40. 40 plus looks good. Just kind of annotate that as you would. And again, there's a little theory comment that you guys can read. Pretty much, we're going to assume normality, but the distribution works out fine anyway. All right, so here is some more work. Again, I'm just trying to get through this real quick so we talk about the exam a little bit. So in this case, you have a variable, a parameter, a mean, a standard deviation, and you find the standard error. The second variable has a second mean, a second population standard deviation, and a standard error. But when you put these two together, which is what we're looking at, the difference in the two, now you just kind of subtract. x1 minus x2 is this guy. So then that makes sense that you'd have mu1 minus mu2 here, x1 bar minus x2 bar there. And if you kind of look here, you have this guy. If you square that, you get a variance. You have this guy, if you square, you get a variance of sorts. But you can't have a 0 or a negative standard deviation, right? So just kind of trust me that you don't take the difference here, but you take the sum, okay? So the difference for the means, but the sum for the standard errors. And that's where that formula comes in down here. So this guy here, my friends, is new standard error for us. We covered the other two earlier in previous chapters. That should be NEW. Okay, so there's that. And that's all we're saying there, okay? So pretty much, we're going to use that in some capacity to get confidence intervals and hypothesis or test statistics. Wow. Good seeing all of you. All right, so let's go ahead and keep on moving. Okay, so you have a point estimate, and now you can find the standard error, right? And so before we had this guy going on, where you have the sample mean and the standard error, and you get this guy here, okay? But the general formula for our purposes, when the standard deviation is unknown, is a point estimate, give or take some t times the standard error. So you can kind of more or less bear with me, if you will. And the point estimate here, use green or blue. There's x bar. So I'm going to bring this whole thing over here, and now that's my point estimate. Okay, so hopefully you can see that there's just an analog here, and we're just changing places. And then plus or minus some t, and then what goes next to the t? Take a wild, crazy guess. It's somewhere on the page. The standard error, yes. And what is the standard error for this situation? That big old square root. Excellent. This guy, right? Perfect. And guess what? We have even a bigger square root down the road. So then the standard error jumped over here before. So now this big old square root, she calls it, is going to insert itself next to the t. So t times the square root of all of this stuff. That's the new formula. And of course, on a test or on a final exam, you will be given that information. So don't worry about memorizing it, but just kind of see where it comes from. Moving on down the road, okay? So then guess what? Chapter 8, or chapter 18, I guess, you had to do with the test statistic. There's the point estimate. There's our good old friend standard error again. So the sample mean shows up right there as the point estimate. The standard error is in the denominator. Oh, look at that. Point estimate minus your hypothesized value over the standard error. So I'm going to say that we're looking at here, assuming that the point estimate of the hypothesized mean is 0, we're looking at a t equaling to x1 bar minus x2 bar, and then that's the point estimate part divided by the standard error. Yeah, how about that? Okay, and then I have this little caveat that we can assume if the mu naught is 0, then it's just the difference in the sample means over the big old square root. I like that very precise term, big old square root, right? Very good, very good. But it gets the point across. All right, so again, for our purposes, will be that the mu1 equals mu2, therefore the difference is 0, and then we just have let's be explicit here. Minus 0, which means it just cancels out, right? So then now we can finish out this table from before. Our point estimate is x1 bar minus x2 bar, and the confidence interval is x1 bar minus x2 bar plus or minus t and this is just s1 squared over n1 plus s2 squared over n2. Give ourselves a little more room to work with. Okay, so there's that. So then now to get the test statistic in there, it's just plug it in. Okay, so there you go. And now we can kind of just plug in numbers, right, and solve equations and that sort of thing. But we had the theory in place, so let's go ahead and keep it moving. Okay, so if you can't quite understand my writing, that's okay, because you have it here formally the way the textbook shows it. And the only thing to think about is that the degrees of freedom now is this character. Remember how before with t we did n minus 1, right? Now we're doing the smaller of n1 minus 1 and n2 minus 1. So the smaller of those two values. Okay, so again, here's a summary right here. That's for the confidence interval. And this is for the test of significance. Very straightforward. Not straightforward, but you can kind of see how it came from previous work that we've done. Okay. You guys heard of Rolling Stones? You've heard of Coldplay? Maybe you've heard more of Coldplay than the Rolling Stones. So here's our situation, revisited. Okay, so if we want to kind of test, is there any evidence to suggest that the mean concert ticket prices is greater for Rolling Stones than for Coldplay? Now that sounds like a test of significance. And so even though the formulas differ for this chapter, the process, step by step, is very relevant to you for things you might come across later on today. So it's probably good that you guys are here. All right, so I have some room to kind of get this going. So let's see here. All right, so I'll use a thinner. How about that? That works. Okay, so let's see. We have here, the first thing we want to do is all the relevant information. And stating the hypothesis in mathematics and verbally, I guess you could say. So, is the mean ticket price for Rolling Stones greater than that for Coldplay? And I'm going to say that we have a mean for our stone. Is that greater than the mean for C play? So that's how I'm going to restate that mathematically. So again, very important, jot down the claim as it appears in words, but then kind of restate it mathematically for your purposes. So the relevant information is that the alpha is 0.05, and then we have some other information. I won't write it down here. But you have it right there in front of you with the sample mean, the standard deviation, sample size, so on and so forth. So I'll come back to that soon enough. Okay. We'll say C table. Okay, so next thing we want to do is get the hypotheses. So the null hypothesis is that the mean for Rolling Stone equals the mean for Coldplay. What will be the alternative hypothesis? That they're not equal to, but in this case they gave us a hint that it's greater than, okay? So then we'll say here the alternative is that the Rolling Stones average is greater than Coldplay's average. Okay? So again, this process so far should be kind of similar to what we've done in the past. Let's kind of do this color. Okay, so the hypotheses are here, and then you have to check these conditions. And again, I will scaffold you through on an exam, okay? So I won't just kind of give you a big open space and say solve it, right? I'll kind of ask you for different things. So the conditions in this case, is it from a random sample? The answer was yes, it was given us from a random sample. We can assume independent samples in this case. That was mentioned earlier. And in this chapter, you will assume normality, but that's also to be given. Okay, so those are the essence of the three issues for the conditions for our purposes. Is it from a random sample? In this case, it's independent, so that takes care of that 20 is a population arbitrarily large issue, right? And then is it from a normal distribution? And if so, what's the sample size? So we're okay in this case for all three of those conditions. Give myself some more room. There we go, that works. All right. So then now we're going to compute the test statistic. And then that was that large formula from before, okay? And the chart organized all that information for us. All right. Whew. So we have all this information here. And you're like, where did you get that information? That's 325 and so forth. That is from this guy. 325.5, 267.9, et cetera, et cetera, et cetera. So this is similar. Hypotheses, conditions, test statistic. And you have a test statistic of 2.177. Probably some evidence to reject the null hypothesis, right? It's kind of in the 2, 3 range, okay? But you still got to go ahead and compare that to something. So if you were to estimate the p-value, which again, that's the step that you guys do in chapter 18 as well, then you want to go to your t-chart, okay? And the sample sizes were 12 and 10. And accordingly, it says the degrees of freedom is the smaller of the 2 minus 1. So the degrees of freedom in this case would be the 9, I guess you could say. Yep. Okay, so if you go to that 9th row in your T chart, okay, 9th row in the T chart, you scroll down, and it should look like this, if I'm not mistaken. You should have a 1.833 and a 2.262, okay? If you go down to 9, you should see those two values. What I'm going to tell you to do for an exam, for a final, or whatever, in this case, for this class, when you see these on your T-chart, and again, if I'm wrong, let me know, then just kind of write in pencil, because you guys will all bring pencils, right? write in pencil whatever test statistic you had. Because 2.177 is in between those two. And then you just use a little bit of reasoning, so to speak. Okay. The corresponding p-values, let's say, if you're to go to the chart, in the t-chart, 1.833 had a one-sided p-value of 0.05. 2.262 had a one-sided p-value of 0.2025. So if your test statistic is in between those two numbers, then your p-value should be between those two probabilities. And then you have your conclusion. Okay, so let's go back to our conclusion. We reject the null hypothesis at the point alpha equals 0.05 level. So then what were we trying to do in the very first place? What was the whole goal? Compare what? We're comparing two distributions. What were the two groups? Ticket prices for Rolling Stone, ticket price for Coldplay. That's why it may seem kind of pedantic, so to speak, but that's why I like to ask you guys to write it out in words in the very beginning so we know what you're looking for. Is the mean ticket prices for Rolling Stones higher than Coldplay? According to this, at this level it is. Okay, and then you can kind of go into your own little thinking of why that could be the case, right? Rolling Stones have an older crowd, been around longer, that sort of thing. Yes?
Regarding the conclusion, though our probability is 0.05, we have to reject the null hypothesis because it's equal to the alpha. Like, what happens if that is the case, if we have one of the p-values equal to that?
Okay, so the question is, in this case, the p-value is less than or equal to alpha.
So it's less than or equal to?
Yes.
So if it was equal to and greater?
Well, if it was greater than, then it's failed to reject.
But if, say, our p-value was 0.05.
On the nose?
Point something larger than 0.05.
If our p-value was 0.05 and our alpha was 0.05, then you could say it's a tie, right? But according to the rule, if it's less than or equal to, we still reject the null hypothesis. Okay? So the tie goes to rejecting the null hypothesis. Now, you may say, oh my gosh, I'm confused. No, don't be confused. Okay? Oh my gosh, this covers something that's not on the test. Not necessarily. What are the key things, right? The key things correspond to making sure you know how to get the problem set up. That's important for today. Okay? Making sure you know what your hypotheses are. That's important for today. Making sure you know the conditions and how to check those. Is it a random sample? Is it from a large enough population? Is it from a small enough, or is your sample, is your population large enough, your sample small enough, sort of thing. So that's that 20 component there. Is it from a normal distribution? Look at the shape of the data. There was a problem in the review sheet that talked about, like, what was it? Oh, what was that problem? The picture, the graph, I can't remember that. It was on the review sheet, okay? This escapes me. What was the problem in the review sheet about the hypothesis test? What's that? Yes, those big guys, right? The sumo wrestlers being like 550 pounds, right? Okay, that's right. I forgot. So, but that had a bell shape, right? Kind of like a bell distribution, okay? So those kind of things. So the key components of this test are still relevant to what you're going to be doing later on today. Conditions, test statistic, p-value, and conclusion. If you see it like this, you're like, what in the world happened, right? But let's kind of enumerate this. So let's call this guy we'll call this like your first step. All the relevant information, okay? Get that kind of going. The second step that's very critical is what in the world is going on with your hypotheses. The third step is kind of like what's going on with your conditions. The fourth step is maybe like a test statistic and then the p-value. And maybe the sixth step is the conclusion. So you had a handout that also scaffolds you through as well. So you can kind of anticipate that I will scaffold you through, hey, give me this. Hey, give me that. Hey, give me that. Okay? So there you go. But we're not done, are we? Because guess what? We're looking for now the confidence intervals if you're not tired from the other stuff, okay? But this is actually more manageable. Well, the formula is, okay, so we'll just say that assume that to be true. And then now we have that formula for the confidence interval. And we're just going to plug in information. We'll hold off on that guy. And we're doing a 90% confidence interval. So the t that you want to use for 90%, and you want the degrees of freedom to be the smaller of n-1, n1 minus 1 and n2 minus 1, so 9. DF tells you how far down to go, the confidence level how far across to go. It should be 1.833. Oh my goodness. Whew. Right? And that's just having done the math ahead of time. If we were to plug this all in, we'd still be typing this the standard error out. One caveat for you guys is be careful when you put this in the calculator. Put a parenthesis, it kind of comes with one already, behind there, order of operations divide by 12 plus this, square that, and then just offset it, and it should still work out. Just be careful. You guys are strong enough, smart enough to, in my opinion, do all this in one step. Don't do 52.5 squared, divide by 12, enter, get some number, plus this, square, divide by 10, square, add them up to the square root. You can do it all in one step, okay? Just especially if you have the TI 83, 84 plus calculators. So, what are we trying to do? We're looking at the difference in ticket prices. We get 9.09 and 106.11. This is in dollars. So the average Rolling Stone concert ticket price is between $9 and $100, $106 more than Coldplay. All right, so we are 90% confident the average Rolling Stone ticket, 2005 concert ticket price is basically $9 to $100 more than Coldplay. Okay, so then I have some caveats. But what's important here? What's important for you for the rest of today, for example? The formula will change a little bit, right? This whole process of saying I'm such percent confident, that's important. That the average is between those two numbers, that's important. Okay? So you guys have the foundation to be successful in inference, whether it's confidence intervals or hypothesis testing. All we're doing now is just changing the situations. One sample, two sample, standard deviation known, standard deviation unknown, that sort of thing. Okay? So closing the door on chapter 20 for now. Chapter 19. Sorry, chapter 19. We will not open up the door on chapter 20 just yet. Okay? And these are things that you can read at your leisure. All right, so how many of you went to the review yesterday? Ooh. All right, and just like we did before, can someone kind of recap the review for, not what you guys covered exactly, but the general sentiments of the review for those who were not there? Is it Daryl? Huh?
Garrett.
Well, you know, Garrett. Garrett, were you there? Okay. So, Daryl, were you there? Wait, are you Daryl? What's your name? Okay. In the blue, your name again?
Raymond.
Yeah. What's up, Raymond?
What's up?
Okay. So, what did you guys do yesterday?
Basically, we just went over the review, and then we covered, kind of went into depth over a lot of the questions and the hypothesis testing, and just basically like nitpicking specific things, like people don't make silly mistakes
Okay.
and stuff like that.
All right. So, silly mistakes will always get you. So you have 15 minutes with me. You can fire at will if you have immediate questions, or you can say, "Why don't you help us?" Right? Yes, ma'am.
I understand that when deciding between using the z-test and t-test,
Okay.
that it depends on whether the standard deviation of the sample or the population is given or not.
Yes.
Um,
So far, so good. You're doing
is there
good.
another way of deciding when to use t or z
Um.
aside from that?
Right.
Oftentimes I notice in your examples, it just says standard deviation in Word, and you're not sure. Do you read it from the example when it says a random sample is given, so then you think random sample, okay, so that's going to be,
Oh, okay.
yeah.
Right. So her question is, how can you determine if it's a sigma
Right.
or if it's just the S?
Yeah.
So when I say information, a random sample has a mean of this and a standard deviation of that, then that's the sample standard deviation SX. Okay, and then it'll have like a sample size of 10 or 15 or whatever the case is. If the population standard deviation is given, I will say sigma equals clearly what it is. Or I will say the population standard deviation is 15, 20. There's a question on the review sheet where you had to do the minimum sample size. Remember that? N equals Z times something. Let's go ahead and pull out the review sheet, I guess, as the way to help us out. There they are, the sumo wrestlers. All right. So come back through here. We'll come back to these guys in a little bit. Math improvement. Come on. Here we go. Okay, so an automobile executive wishes to estimate the mean number of miles, minimum sample size, and then there it says explicitly sigma is 1970. So that one's pretty clear about what the standard deviation is. This one is not clear,
Yeah.
right? Nothing's given about these big old guys, right? So, but when I throw in the mean, standard deviation, all this information here, it pertains to the sample, and so yeah, you can assume that that's SX. That's the sample standard deviation. Okay. So if I give you data, assume sample standard deviation. Assume T, right? So there's that one. I think this is important. All right. So let's see here. Here are the steps, right? So state the claim that requires a test. It is or it is not 550. That should be no problem for you. Okay. What kind of conditions are we working with? All right. So again, there are probably a ton, but of sumo wrestlers out there. And yes, there's that chart that talks about if it's less than 15, you have to look for normality and skewness. If it's between, we just talked about this earlier, right? Less than 15, that chart makes it seem like it's so difficult, but it's not that difficult. If it's less than 15 for your sample size, you need normality, skewness, outliers issued. But then when you get between 15 and 40, the normality kind of falls off more or less, and you look for skewness and outliers. When you get to 40, 40 is your magic number, right? You get to 40, it's all good. All right?
I have a question. Totally random.
Yes.
Does that having n equal greater than 40, does that go back to the central limit theorem?
Yes.
So, the greater the n is. Okay.
Yes, and then there's a few graphs where the t kind of converges to a z. So yes, that's where the question comes from. Similar question? You had your hand up, sir? Oh, you didn't? In the black? No? Oh, okay. All right. Sorry. So then you find the sample mean compared to the hypothesized value. Get some test statistics. And again, I would compare to see if it's between these two numbers, right, on the chart. So let's just be clear, all right? Let's just make sure we know how to do this, work with this chart, because I'm still not totally sold on this, all right? So everybody, get out your T-charts, please. I know it may seem like I'm trying to be picky here. Yes, ma'am?
So when you check the conditions, do you need to explain why the sample's small enough and why it's large enough, or just write it up?
I think no more than that explanation is fine. So like if you were to say there's an infinite number of sumo wrestlers, that's fine with me for the middle condition. So please get out your T-charts. I hate to be like a third grade teacher here, but I want to make sure you guys get it so you don't get it wrong, right? Right. All right, so let's just make sure that we're on the same page here. Okay, so the exam review says that we have 19 big old sumo wrestlers. You go back down to the 18th row, all right? So the 18th row is for the degrees of freedom of 18. And so I'm going to look at the value that's between, for my test statistic. Bring this down, I'm not that tall. 18 would be between those two. We had a test statistic of 3.197. Okay, or 3.58, excuse me, 3.58. So 3.58 for 19, or 18, excuse me. Oh, this is even better. 3.58 is in between those two, right here. You guys see that? Please say yes. Okay, thank you. Right, 'cause I want you to get it right. You want to get it right?
Yes.
Okay, we're not getting fired up for a game or something like that. But we got a game today, all right? Let's go. I'm getting pumped. Oh, sorry. So 3.197 is right here. 3.611 is right here. What I would do on the test, whenever, tonight, tomorrow, the final, whatever, I would write out 3.58 in between there, right there. Write it in pencil, whatever. And then now, can I do it on this thing? Yeah, I guess so. We'll be explicit. .58 is in between those two numbers. So then when I go down to the bottom of the chart, the one-sided p-value is in between those two numbers. Oh, I'm sorry, we had two-sided tests. My fault. We had a two-sided test, so the p-value is between those two numbers, 0.002 and 0.005. So now you can kind of see how it all works together. Your test statistic is in between those two numbers. Your p-value is between those two numbers. If it's a one-sided test, then obviously you do the upper row. Okay, other information in the last few minutes that we have together. That looks like a normal distribution to me. T is fine. Okay, and again, the standard deviation is 9.84. It doesn't say sigma is 9.84, so but yet it's accompanied by the sample mean. So I put all the sample information all together. Hand up.
What's the difference between finding the z-statistic where it says choose 1 to random, what is the probability that student scores between 22 and 28?
Okay, so I heard 22 and 28.
What, yeah, when it says like find what is the probability that the student scores between those two numbers, like when do you use x bar minus
Ooh.
over
All the rest of that stuff, right?
versus z equals x bar minus the mean over standard deviation? Like the long one versus that short.
I like that phrase, a long one versus a short one. This is an important question. So, I think it's one of these guys.
Yeah, the ones I was talking about was 18A and 17B. You use different equations to do those.
Okay, my equation didn't quite come through. So, who can answer that question first? How about that? Because this is important. All right? If I'm talking about an individual, like one person, the probability that Joe has some kind of range of outcome. So for one person, then it's just x minus the mean over the standard deviation. Like the previous test, right? We did that in the previous test. But when we look at the sample mean, so the key word is this guy. Can I write on here? Well, you get the idea, right? The key word is sample mean. Now all of a sudden, I got to look at the standard deviation over radical n. Okay, that's very important. Important. Echo. All right. So that's something to keep that in mind. And oh, here it is. Yeah. A single student, you just use the regular z-score. The average, now you got to do that standard deviation of radical n.
If it was one person,
Yeah.
why it was a different equation.
Yes. Okay. On your mark, get set, go get them. Yes, same formula sheet. Yes.